Hello folks, today we'll be going over a lesson of the ideal gas law. Today in this lesson we'll be covering basics of gases as a review, what ideal gases are, their formulas and equations, the graph relations between their properties, the properties, real world applications, and then lastly a conclusion that summarizes it all. Basics of gases. As we know, gas is a state of matter, right? The gases are their molecules and atoms are larger apart, like in this picture, compared to solids and liquids, which allows gas to take up the volume of its container. Gases, when heated up, move faster. They have three main components to be measured by: volume, temperature, and pressure. Right? Pressure is a force exerted by their atoms when under different temperatures in different scenarios. Volume is obviously the mass of which the gas takes up, and the temperature affects the pressure and volume of molecules. As when the temperature is increased, the particles get more excited, have more energy, and tend to move faster and farther apart. So those are the three main components, and this is basically like the basics of gas. Formula for the ideal gas law is PV equals nRT. This formula here allows us to basically understand the different pressure, volume, and temperature, and how it affects gases in different scenarios. So what it stands for: P stands for pressure, V stands for the volume, N stands for the moles or the amount of a certain component or element, R stands for the gas constant, and T stands for temperature, the gas constant. Basically, the gas constant is the proportionally constant that connects the temperature and substance amount levels in physics to energy scales. The gas constant is universal and stays the same. It is represented as 0.082 liters atmosphere to moles in Kelvin. And basically, if we are measuring the pressure in atmospheres, it stays like that. But if we're measuring the pressure in pascals, it becomes 8.2. So we move the decimal 2 places over, and the formula is written as liters, kpascals, and then moles in Kelvin. Lastly, temperature. Temperature obviously is the temperature of the area, which affects obviously the particles and the gas and how they move and the volume they take up. Temperature is measured in Kelvin. So if we have Celsius, we add 273.15 to it, and that gives us Kelvin, which we then input into the formula. Graph the equations and the relationship between pressure, volume, and temperature, the three main components of the gas. This is what we get. So for the volume constant, the relationship between pressure and temperature and volume, it's linear, y equals mx, right? Because the greater the pressure and the greater the temperature, the greater the volume, right? And so it just adds an upward trajectory, and it's very similar with the pressure constant, right? Y equals mx is the linear equation, and when the volume is greater, the temperature is greater, the more pressure there is, right? Because for this one, obviously with more pressure and more temperature, the gas particles move more, and because of this, they take up more volume. And for this one, for the pressure constant, right, with more volume and more temperature, right, the pressure is greater. And then lastly, the temperature constant. This one's the only one that's different. Y equals mx to the -1 power. It's inverse function, and this is basically the pressure and volume relationship. Shows temperature, and it's an inverse linear line. So these are the three graphs that show the relationships between temperature, pressure, and volume, and basically they're linear equations. So we're gonna do a little problem here. We're gonna do a little problem here and basically show how we use the formula PV, or the ideal gas law PV equals nRT, to find variables that we don't know. Right? A lot of the time we use this formula to find variables that are not present in a scenario to try to like predict what they'll be. So in this scenario here, we're given pressure, which is 2 atmospheres. Volume is unidentified, which is what we need to find. The moles is 1 mole, the temperature is 278 Kelvin, and the ideal gas constant is obviously always the same, 0.0821. With this here, we basically want to isolate the variable using this formula. Okay, and to isolate it, because we already have P and V separate over here, we're basically just going to bring the P over, right, and divide it by nRT. So it's going to look like that's the formula we're going to get. And basically, when we're trying to find an an identified property, we want to isolate it by itself and then plug in the numbers that we have, which is the given on this side, and isolate it, and by doing that we should find it. So I'm going to do this example very quickly and then I'll walk you guys through it. Okay, so let's walk you through it. So we input the numbers, the amount of moles, the real gas constant temperature up here, and the pressure down here, right? And so then we basically just multiply these together, which gives us 22.82, and then we divide it by the pressure, which is 2, and that gives us 11.41 liters. This is a much more simpler version, just to kind of give you the ideas of it, but it's basically isolating the variable and then solving with what we're given. And so in this equation, we get 11.41 liters, and so that would be the volume. We're going to talk about like real world appliances with ideal gas law. So I'm going to take you through 3 different ones. I'll obviously look at my great artistic skills. I don't know if you can tell, but this one is basically represents a scuba diver. And the reason why this formula and theory is very valuable for scuba divers is because when they're going down, especially to like either do research or just for like the fun of scuba diving, the pressures increase the lower you go in the ocean, obviously in bodies of water. And so with that, when that happens, naturally the lungs decrease and humans aren't able to hold the same amount of air that they are at normal pressure levels, like above water. So using this formula, they're able to calculate what the pressures are and temperatures, what volume of gas the scuba diver needs in their tank to help them last down there, right? Especially for the time that they're going down there. So it's very helpful in allowing scuba divers to understand the depths they're going to, the pressure there, and how much that's going to affect them and how much air they're going to need to bring with them when they go down, so obviously they don't end up running out of air. So yeah, scuba diving is definitely one of the more impactful ones that relies on the ideal gas law, because it's just so valuable, and they kind of, without it, they wouldn't be able to know what to do in certain scenarios in terms of how much air they need and the different pressures they're going to experience when they get. So with the next picture here, it's car. So with cars, the automobile engines is when they use ideal gas laws, basically understanding the pressure needed to in the pistons in the combustion engine, which is basically where the power of the car is created, knowing what pressures and what the amount of mixture needed to get the reaction they want. And so using ideal gas law, they can figure out some sort of idea of what they need and what is required to create that energy that allows the cars to run. So lastly, the third one here, if you can tell or not, it's a refrigerator. Refrigerators rely on ideal gas law to basically regulate how the fridge cools itself using pressure, volume, and temperature. And using ideal gas law allows the fridge to basically create technology that manages it, so it knows when to cool down and release more, cold air or a cooling device to basically help cool down the food, or at least keep it cool. So yeah, refrigerators, scuba, and automobiles are the 3, I'd say, biggest technologies and scenarios that use the ideal gas law. The ideal gas law is seen in a bunch of other examples, such as like air balloons, and stuff like that. But these are the 3 I decided to go into. The ideal gas law is used universal, and it's definitely a main importance in gas and science and technology. So now we're gonna go watch a demo on using the ideal gas law in real life. So,
hi. So today we're gonna be doing the hot water bottle ideal gas experiment. So the required equipment, we're going to be using a 2-liter plastic bottle, soda pop bottle. We're going to be having a 300 milliliter cup of hot tap water, and this bowl here is just for what we're going to do with the water afterwards. So the procedure of this experiment is you're going to take the bottle, you're gonna pour the water into the bottle. You're gonna cap it with your hand, so take the cap off, cap it with your hand, and you're gonna shake it quite a bit. And then after you're done shaking it, you're gonna take your hand off, pour out the water, and you're gonna put on the cap very quickly. After that, you're gonna sit and you're gonna watch to see the reaction it gives us. So now it's time for the experiment. So we're gonna pour this water carefully into the bottle. Try not to make a mess like I just did, but you're just pouring the water in there. Okay, so now we're gonna quickly put our hand over it. Right, we're gonna quickly pour out all the water. Now we're just gonna watch. As nothing happens. Oh, wait. Pass it. We look here, actually. The bottle is starting to kind of curve in. A little bit there too now. And gradually, as the temperature gets back to normal, the bottle will expand back to its original shape. But yeah, see, now you can really tell how the insides are dented in and it's taking a different shape. So relating this back to the ideal gas law, what we saw happen in this experiment. So when we poured in the hot water created an increase in temperature. And with the relationship between temperature and pressure, that also created an increase in pressure. After we dumped out the water, hot water into here, what happened was the bottle, right, still had the hot temperature and hot pressure in the air, but slowly, as it cools down, what ends up happening is the bottle starts to crush because the external pressure is still the same, but the decrease in temperature over time and the decrease in the pressure causes the external pressure to kind of cave it in. And so as a result of this, we see how the shape is different and it's a bit thinner on the sides. But over time, actually, this will just stay like this, right? Because we still have the external pressure on the bottle and the internal pressure and the internal temperature is slowly decreasing. And so that's basically a scientific explanation of what happened here, relating it back to the ideal gas law. And so yeah, that's basically the experiment. And so actually at first I didn't think we were gonna get a reaction, but as you can tell, actually over time it got a lot better, right? It's more intense. So yeah, this is the final result of our experiment. Give me a little update on the bottle. I've just let it kind of sit and it actually is increasingly getting more and more crushed, right? Because as it cools down, the external pressure is greater than the internal pressure, which is causing it to kind of collapse in like that. So I just thought I'd get a little update going.
To wrap up our lesson on ideal gas law, we learned about the basics of gases, which I think everyone really knows. But going to ideal gas law, the formula PV equals nRT, right? P stands for pressure, P stands for volume, N stands for the moles, R stands for the real gas constant, and T represents temperature. We learned that basically that formula allows us to see the different relationships, especially between pressure, volume, and temperature, which are the three main properties of gas that are measured. And then so we went into the graph, and that shows the relationships between pressure, volume, and temperature, as well as we talked about how to find unidentified variables by isolating the variable in the formula. And then we did an example, right? And we then lastly finished off with real world appliances, such as scuba diving, automobiles, and refrigerators. Obviously, there's a lot more. Those are the three I went through. And so, yeah, the ideal gas law is seen in everyday things, whether we realize it or not. It's a really good tool in terms of understanding the relationship between pressure, volume, and temperature of gases, which obviously are always around us. And so, yeah, thank you for tuning into this lesson. There is a worksheet that follows this lesson if you'd like to go through that. So thank you again, and this is Ideal Gas Laws.